Welcome back to be inspired from life. When we observe the world around us, everything appears solid, continuous, and predictable. A ball rolls across the floor, a glass shatters when dropped, light travels in straight lines and casts shadows. These experiences train the human brain to expect certainty. Cause leads to effect, objects occupy a clear position, and nothing exists in two states at once. For centuries, this way of understanding reality felt complete. Classical physics explained motion, gravity, and light well enough to build machines, bridges, and even send humans to the moon. Yet beneath this familiar surface lies a realm so strange that it defies intuition entirely. At the smallest scales of existence, the rules change. The universe no longer behaves like a solid machine. Instead, it behaves more like a shifting field of probabilities. Particles do not behave only as particles, and waves do not behave only as waves. They blur into something entirely new, something that challenges the very meaning of position, motion, and reality itself. This discovery did not arrive easily. It emerged slowly through confusion, contradiction, and experimental surprises that refused to fit into existing theories. Light was the first major clue. For a long time, scientists debated whether light was made of particles or waves. Waves made sense because light could bend, interfere, and spread out. But particles made sense because light could knock electrons out of metal surfaces, a phenomenon that waves alone could not explain. When experiments proved that light behaved as both, physics faced a crisis. Something fundamental was missing from the old understanding of nature. That missing piece was quantum mechanics. It introduced a radical idea. At the smallest scales, entities do not belong to a single category. Electrons, photons, and other fundamental components of reality are neither particles nor waves in the classical sense. They are quantum objects, capable of behaving as either, depending on how they are observed. This dual behavior is not a metaphor. It is measurable. When electrons are fired one by one at a screen with two narrow slits, they create an interference pattern, something only waves should do. But when those same electrons are detected individually, each one arrives as a single point, like a particle. There is no gradual transition between the two behaviors. The same object displays both properties without contradiction, as if reality itself adapts to the question being asked of it. This behavior becomes even stranger when we consider what happens between observations. In the quantum world, particles do not travel along clear paths. Instead, their behavior is described by a wave function, a mathematical object that represents probabilities rather than certainties. Until a measurement is made, a particle does not have a single definite position. It exists as a spread of possibilities, occupying multiple potential states at once. This idea is deeply unsettling because it contradicts everyday experience. A chair is either in one place or another. A door is either open or closed. But at the quantum level, an electron can exist in many places at once, not metaphorically but mathematically and experimentally. Only when it interacts with something large enough, such as a detector or a measuring device, does it appear to choose a single outcome. This difference between particles and waves explains why matter behaves so differently at small scales. A classical particle cannot pass through a wall unless there is a hole. A wave, however, can spread out, bend around obstacles, and leak into regions that would be forbidden to a particle. Quantum objects inherit both abilities. They can strike a barrier like a particle and still behave like a wave that extends beyond it. This is not because the particle breaks the wall or finds a crack. It is because the wave aspect of the particle does not stop abruptly at boundaries. It decays gradually, meaning there is always a chance, however small, that the particle will appear on the other side. This is not a violation of physics. It is physics operating under rules that are fundamentally different from the macroscopic world. The reason we do not observe these effects in everyday life is scale. The wave-like nature of matter becomes more pronounced as objects become smaller. For large objects, like humans or cars, the wavelength associated with their motion is unimaginably tiny. Any wave-like behavior is effectively cancelled out, leaving only classical motion. But for particles like electrons, the wavelength is large enough to produce measurable effects. This scale dependence is critical. It explains why walls appear solid to us but not necessarily to certain particles. It explains why light can reflect off surfaces while neutrinos pass through entire planets. It explains why classical intuition fails when applied to atoms and subatomic particles. At small scales, energy also behaves differently. Instead of being continuous, energy comes in discrete packets, known as quanta. This quantization affects how particles interact with matter. An electron bound to an atom can only absorb or release specific amounts of energy. If incoming energy does not match one of these allowed values, it simply passes through. This selective interaction further blurs the line between wave and particle behavior. Time itself behaves differently in quantum systems. Events do not unfold as a smooth sequence, but as probabilistic transitions between states. A particle does not move from point A to point B in a straight line. Instead, it explores all possible paths simultaneously, with some paths being more likely than others. This idea, formalized in quantum path integrals, suggests that reality does not choose a single history until it is observed. The implications of this behavior extend far beyond walls and particles. They challenge the idea of objective reality. If particles do not have definite properties until measured, what does that say about the nature of existence? Is reality fundamentally incomplete without observation? Or is observation simply a way of interacting with a deeper, hidden structure? These questions are not philosophical distractions. They influence real technologies. Semiconductors, lasers, MRI machines, and quantum computers all rely on the wave-particle duality of matter. Without accepting that particles behave differently at small scales, modern technology would not exist. Yet despite its success, quantum behavior remains deeply counterintuitive. Even the scientists who developed the theory struggled to accept its implications. Some argued that quantum mechanics was incomplete. Others believed that hidden variables must exist beneath the randomness. But decades of experiments have confirmed that nature truly behaves this way. The universe does not reveal itself fully unless forced to do so by measurement. This brings us back to the central idea: particles and waves behave very differently at the smallest scales, and this difference is not a minor detail. It is the foundation of why the universe works the way it does. Walls are not absolute barriers. Solidity is not fundamental. What we perceive as firm and impenetrable is the result of countless quantum interactions averaged over enormous numbers of particles. At the microscopic level, reality is flexible, uncertain, and deeply interconnected. Particles are not tiny objects moving through empty space. They are excitations of underlying fields spread across space, responding to probabilities rather than certainties. Their wave-like nature allows them to explore regions forbidden to classical objects, while their particle-like nature allows them to leave precise, measurable traces. This dual behavior is not a flaw in our understanding. It is a feature of the universe itself. The small does not obey the rules of the large. Instead, the large emerges from the small through sheer numbers and statistical stability. What feels solid is, at its core, a delicate balance of forces and probabilities. Understanding this is the first step toward understanding why some particles pass through walls while light does not. The answer does not lie in strength or weakness alone, but in the fundamental nature of reality at its smallest scale. A reality where particles are waves, waves are probabilities, and certainty is the exception, not the rule. At first glance, the world appears dense and solid. Walls resist pressure, floors support weight, and objects collide with unmistakable force. This experience convinces us that matter is tightly packed, that solidity is a fundamental property of things. Yet this impression is one of the greatest illusions produced by human scale. When we descend into the atomic world, solidity dissolves, and what remains is a universe dominated not by substance, but by space. Every object around us, from mountains to machines to the human body, is built from atoms. These atoms are unimaginably small, but their internal structure is even more astonishing. An atom consists of a nucleus, made of protons and neutrons, surrounded by electrons that exist in regions far from the center. The nucleus contains most all of the atom's mass, yet it occupies a volume so tiny that it barely registers in comparison to the overall size of the atom. To grasp this emptiness, scale becomes essential. If an atom were expanded to the size of a football stadium, the nucleus would be no larger than a grain of sand at the center. The electrons would not orbit like planets in neat paths. Instead, they would exist as probability clouds spread across the vast space of the stadium. Everything in between would be empty. No solid substance, no rigid filling, just space. This means that more than 99.9999% of matter is empty space. The solidity we feel does not come from physical contact between solid pieces. It comes from invisible forces acting across empty regions. When you press your hand against a wall, the atoms in your hand never truly touch the atoms in the wall. Instead, the electromagnetic forces between electrons repel each other so strongly that the atoms resist being pushed closer together. This repulsion is what your brain interprets as hardness. The sensation of touch is not the result of contact, but of force. You are feeling the resistance of electric fields, not the presence of solid material. In a very real sense, you are interacting with empty space structured by forces. This revelation transforms the idea of barriers. A wall is not a continuous slab of matter. It is a lattice of atoms separated by enormous relative distances, held in place by electromagnetic bonds. For large objects like humans, these forces are insurmountable. Our atoms are bound by the same forces, and the repulsion between them prevents overlap. But for certain particles, the story is very different. Subatomic particles do not experience matter the way we do. Their size, energy, and interaction strength determine whether they are stopped or allowed to pass through. Some particles interact so weakly with atoms that the emptiness of matter becomes an open pathway rather than an obstacle. Neutrinos are the most dramatic example. These particles have almost no mass and no electric charge. They pass through the Earth as if it were transparent. Trillions of them stream through your body every second, produced by the sun, distant stars and cosmic events, billions of light years away. They pass through walls, oceans, and planets without resistance, because the empty space inside atoms leaves little chance for interaction. This does not mean neutrinos slip between atoms like dust through a net. Instead, they move through the quantum fields that make up reality, barely affected by the forces that define matter. The emptiness of atoms means that unless a particle interacts directly with a nucleus or an electron, it will continue on its path uninterrupted. Even particles that do interact more strongly can sometimes pass through matter. High-energy muons, created when cosmic rays strike Earth's atmosphere, routinely pass through buildings and mountains. Specialized detectors deep underground observe them passing through layers of rock that would seem impossibly thick by everyday standards. Again, the reason is not that matter is weak, but that it is mostly space. This emptiness also explains why density is not the same as impenetrability. Lead feels heavy and solid, yet it is just as empty at the atomic level as wood or air. The difference lies in how tightly its atoms are packed and how strong the forces between them are, not in the amount of space inside them. The atomic structure of matter also reveals why light behaves differently from certain particles. Light interacts strongly with electrons. When photons encounter the electron clouds of atoms, they are absorbed, reflected, or scattered. The emptiness of matter does not help light pass through opaque object, because the electrons form an effective barrier through constant interaction. But particles that do not respond to electromagnetic forces are not stopped by these electron clouds. To them, the wall is not a wall at all. It is a sparse field of isolated centers of interaction separated by vast regions of nothing. This idea challenges one of the most basic assumptions of human intuition, that solidity is fundamental. In truth, solidity is emergent. It arises from the collective behavior of enormous numbers of atoms and the forces between them. Remove those forces or reduce the scale of the interacting object and solidity vanishes. At the atomic level, even position becomes uncertain. Electrons do not occupy fixed locations. They exist as probability distributions, meaning that the space inside an atom is not neatly organized. It is dynamic, fluctuating, and governed by uncertainty. This adds another layer to the emptiness of matter. Not only is there space between particles, but even the particles themselves are spread out rather than sharply defined. This uncertainty is not a flaw in measurement, it is a fundamental feature of nature. The more precisely we try to locate an electron, the less we can know about its momentum. The atom is not a miniature solar system, it is a quantum structure defined by probabilities rather than trajectories. When many atoms come together to form a solid object, their collective electromagnetic forces create rigidity. But this rigidity exists only at large scales. At small scales there are gaps, fluctuations and probabilities. The wall that stops your hand is not a continuous surface. It is an averaged effect of countless interactions. This understanding reshapes how we think about boundaries. Boundaries are not absolute lines in space. They are regions where interactions become strong enough to prevent passage for certain objects. Change the object, change the interaction, and the boundary disappears. This is why advanced imaging techniques can peer through solid matter. X-rays pass through soft tissue but are absorbed by bone. Neutrons penetrate metals that stop X-rays. Each probe interacts differently with the atomic structure of matter, revealing that what blocks one thing may be transparent to another. The emptiness of matter also explains why compression has limits. When matter is compressed, atoms are pushed closer together, but they resist fiercely. This resistance does not come from solid cores colliding. It comes from quantum mechanical principles that forbid electrons from occupying the same states. The so-called solidity of matter is, again, a rule enforced by quantum laws, not physical fullness. In extreme environments such as neutron stars, even this resistance is overcome. Atoms collapse, electrons merge with protons, and matter becomes something entirely different. This shows that even the structure of atoms is not permanent. What feels unbreakable on Earth can be undone under different conditions. Understanding that matter is mostly empty space does not make the world feel less real. Instead, it makes it more extraordinary. The universe builds solidity out of emptiness, structure out of space, and stability out of probability. What we experience as firm and reliable is the result of delicate balances maintained by invisible forces. This perspective also deepens our understanding of why certain particles can pass through walls. They are not violating the structure of matter, they are revealing it. They show us that walls are not monolithic barriers but porous systems at the smallest scales. The emptiness of matter is not a weakness, it is a feature that allows complexity, motion and interaction. Without it, atoms could not bond, chemistry could not exist, and life could not arise. Space within matter is what makes matter functional. At human scales, this emptiness averages out into solidity. At particle scales, it becomes opportunity. The universe does not change its rules, it applies them differently depending on scale, and in doing so, it reveals a hidden truth. The solid world we trust is built almost entirely from nothing at all. In the everyday world, barriers are absolute. A closed door blocks a person. A wall stops a moving object. A mountain cannot be crossed without climbing over it or cutting through it. These rules feel so fundamental that they appear woven into reality itself. Classical physics reinforces this intuition by insisting that an object must possess enough energy to overcome a barrier. If it does not, it stops. End of story. Yet when we enter the quantum world, this certainty quietly collapses. Barriers lose their authority. Energy no longer dictates outcomes with absolute finality. Instead, probability takes control, and particles begin to do something that appears impossible. They pass through barriers they do not have enough energy to cross. This phenomenon is known as quantum tunneling, and it is not rare or theoretical. It is one of the most basic and unavoidable consequences of quantum mechanics. Without it, much of the universe as we know it would not function. Stars would not shine, electronics would not work, even life itself would unfold differently. To understand tunneling, we must abandon the idea that particles are tiny solid objects traveling along fixed paths. In quantum mechanics, particles are described by wave functions. These wave functions do not tell us where a particle is, but where it might be. They assign probabilities to locations, spreading the particle's presence across space rather than confining it to a single point. When a quantum particle approaches a barrier, something extraordinary happens. In classical terms, the particle hits the wall and stops. But the wave function does not stop abruptly. It penetrates the barrier, decaying gradually rather than vanishing. On the far side of the barrier, the wave function may still exist, though weaker. This means there is a non-zero probability that the particle will be found on the other side. If the particle is detected beyond the barrier, it appears as if it has passed straight through. No hole, no damage, no delay. The particle simply reappears where it should not be allowed to exist. This is not a trick of measurement. It is not a loophole. It is not the particle borrowing energy or cheating the laws of physics. The particle never crosses the barrier in the classical sense. Instead, its wave-like nature allows it to exist on both sides at once, until observation forces a single outcome. The word tunneling is misleading because it suggests a physical passage carved through matter. In reality, nothing is carved. The barrier remains intact. What changes is the probability landscape. The barrier becomes a region where the particle is unlikely to exist, but not forbidden to exist. This distinction is subtle but profound. Classical physics deals in impossibilities. Quantum physics deals only in probabilities. If something is not explicitly forbidden by the laws of quantum mechanics, it is allowed to happen, no matter how unlikely. The likelihood of tunneling depends on several factors. The thickness of the barrier matters. The higher the barrier's energy, the less likely tunneling becomes. The mass of the particle also plays a role. Lighter particles tunnel more easily than heavier ones. This is why electrons tunnel readily, while everyday objects do not. For macroscopic objects, the probability of tunneling is so small that it might as well be zero. The mathematics allows it, but the universe does not give us enough time to ever observe it. For subatomic particles, however, tunneling is not only observable, it is unavoidable. Inside atoms, tunneling shapes reality. Electrons do not orbit nuclei like planets. They exist in energy states defined by probability. These states extend beyond the regions where classical physics would confine them. As a result, electrons can appear in regions that classical rules would forbid. This behavior allows chemical reactions to occur. In many reactions, particles must cross energy barriers to rearrange bonds. Classical physics predicts that these reactions should occur far more slowly than they do. Quantum tunneling provides the missing explanation. Particles tunnel through energy barriers, accelerating reactions that would otherwise be nearly impossible. In biology, tunneling plays a silent but essential role. Enzymes rely on it to speed up reactions inside cells. Without tunneling, the chemistry of life would crawl at a pace too slow to sustain complex organisms. Life depends not just on energy, but on probability. Tunneling is also responsible for radioactive decay. When an atomic nucleus emits an alpha particle, the particle does not have enough energy to escape the nuclear force holding it inside. Classical physics predicts it should remain trapped forever. Yet it escapes. It tunnels through the nuclear barrier, appearing outside the nucleus without breaking it. This process governs the stability of matter and the ticking of radioactive clocks. The decay rates of elements, which allow scientists to date ancient rocks and fossils, are determined by tunneling probabilities. The deep history of Earth is written in quantum uncertainty. In the heart of stars, tunneling becomes cosmic. The temperatures inside stars are not high enough by classical standards to force atomic nuclei close enough to fuse. The electrical repulsion between positively charged nuclei should keep them apart. Yet fusion happens. Stars burn. Light fills the universe. Quantum tunneling allows nuclei to cross this repulsive barrier, Even though the probability is low for any individual collision, the sheer number of particles inside a star ensures that fusion occurs continuously. Every ray of sunlight reaching Earth owes its existence to tunneling. On human scales, tunneling enables modern technology. The scanning tunneling microscope, one of the most powerful tools in science, relies entirely on this effect. By bringing a sharp metal tip extremely close to a surface, electrons tunnel between the tip and the material. By measuring this current, scientists can image individual atoms. Semiconductors, which power every computer and smartphone, depend on tunneling as well. Transistors, diodes, and memory devices all exploit quantum behavior to control electrical currents. The digital world rests on particles slipping through barriers they should not cross. Even when we do not design for tunneling, it shapes outcomes. In extremely small electronic components, tunneling can cause unwanted leakage currents, placing limits on how small technology can become. Engineers must now contend with quantum effects that once belonged only to theory. This brings us back to walls. A wall is an energy barrier formed by electromagnetic forces between atoms. For most particles, this barrier is effective, but for quantum particles, especially those with low mass or weak interactions, the barrier is not absolute. Tunneling does not require emptiness. It does not rely on gaps between atoms. Even a perfectly uniform barrier can be tunneled through. What matters is the wave function's ability to extend into forbidden regions. This is why tunneling cannot be explained by imagining particles squeezing through spaces. The phenomenon remains even when no such spaces exist. It is a property of quantum fields, not physical holes. The unsettling implication is that boundaries are not real in the way we imagine them. They are statistical constructs. They describe where particles are unlikely to be found, not where they are impossible to be found. This idea forces a reconsideration of control and predictability. In the quantum world, outcomes are not guaranteed. They are distributed. Even if a particle has only a 1 in a billion chance of tunneling through a barrier, that chance is real. Given enough time or enough particles, the improbable becomes inevitable. This probabilistic nature does not mean the universe is chaotic. Quantum mechanics is precise, mathematical, and reliable. What it abandons is determinism, the idea that the future is fixed by the present. Instead, it offers distributions, likelihoods, and tendencies. Quantum tunneling reveals that nature values possibility over certainty. It allows systems to explore outcomes that classical rules would prohibit. It is a reminder that reality is not confined to what seems reasonable at human scale. For walls, for barriers, for boundaries of all kinds, tunneling delivers a quiet lesson. What blocks one form of existence may be permeable to another. What seems absolute may only be likely, and what feels impossible may simply be improbable. At the smallest scales, the universe is not built from solid limits but from flexible probabilities. Quantum tunneling is one of the clearest demonstrations of this truth. It shows us that particles do not ask for permission to exist on the other side of a barrier. They only need a chance. What ultimately decides whether something passes through a wall is not size, speed, or strength in the everyday sense, but interaction. At the deepest level, the universe is governed by forces, and every particle carries specific properties that determine how strongly it responds to those forces. Walls are not obstacles because they are thick or heavy. They are obstacles because of how their internal forces interact with whatever approaches them. To understand this, we must strip a wall down to its most fundamental components. A wall is made of atoms, and atoms are structured systems held together primarily by electromagnetic forces. Protons in atomic nuclei carry positive electric charge. Electrons carry negative electric charge. The attraction between these opposite charges holds atoms together, while the repulsion between like charges prevents them from collapsing into one another. This electromagnetic force is extraordinarily powerful at small scales. It is responsible for chemistry, solidity, friction, and the sensation of touch. When you lean against a wall, you are not pressing against solid matter in a mechanical sense. You are pushing your atoms into regions where electromagnetic repulsion rises steeply. and that repulsion pushes back. Your body, like the wall, is composed of charged particles. Electrons in your atoms repel electrons in the wall's atoms. This mutual repulsion creates an effective barrier that feels solid and immovable. The wall does not stop you because it is full. It stops you because its forces respond strongly to yours. Now imagine an object that does not carry electric charge, or carries it in a way that does not easily interact with electrons. Suddenly the wall loses much of its authority. The barrier that once felt absolute becomes weak or even irrelevant. This is why some particles pass through walls effortlessly. Neutrinos, for example, carry no electric charge. They do not feel electromagnetic forces. As a result, the vast network of electric fields inside a wall barely registers their presence. They move through as if nothing were. Even particles that do carry charge can behave differently depending on how they interact with forces. An electron interacts strongly with electromagnetic fields, which is why electrons are easily stopped by matter. A proton, which is much heavier and also charged, behaves differently, requiring more energy to be deflected or absorbed. The key insight is that walls do not block objects universally, they block specific interactions. A wall is opaque to light because photons interact strongly with electrons. It is transparent to neutrinos because neutrinos barely interact at all. It is partially transparent to X-rays because X-rays interact differently depending on energy and material. Every force has a range and a strength. Electromagnetism has an infinite range and dominates interactions at atomic scales. The strong nuclear force holds nuclei together, but acts only over extremely short distances. The weak nuclear force governs certain types of particle decay and interaction, and gravity dominates at large scales but is negligible between individual atoms. When a particle approaches a wall, the outcome depends on which forces come into play. If the particle couples strongly to electromagnetic fields, it will almost certainly be stopped, reflected, or absorbed. If it does not, it may pass straight through. This is not a matter of intelligence or choice. Particles do not decide what to interact with. Their properties dictate the forces they respond to. Charge, mass, spin, and energy determine everything. Light provides a revealing example. Photons are massless and electrically neutral, yet they interact strongly with matter. This seems contradictory until we consider that photons interact with electric charge, not by carrying charge themselves, but by exciting charged particles. When light strikes a wall, it agitates the electrons in the atoms. Those electrons absorb the energy and re-emit it in different directions or frequencies. The photon does not pass through because it cannot avoid interaction. Change the frequency of light, however, and the interaction changes. Visible light cannot pass through a metal wall, but gamma rays can. The wall has not changed, the force has not changed, the interaction probability has. This reveals a subtle but crucial truth. Forces are not binary. They do not simply exist or not exist. They operate through probabilities. A particle may have a small chance of interacting with a given force under certain conditions, and a much larger chance under others. Walls are therefore probabilistic filters. They allow some things through, block others, and partially affect many more. What we perceive as absolute solidity is simply the outcome of overwhelmingly high interaction probabilities for objects like us. The same logic applies to sound. Sound waves pass through walls by transferring vibrational energy from atom to atom. The wall resists this motion but does not eliminate it entirely. The interaction weakens the wave but does not forbid it. For charged particles, the story becomes even more complex. Electric and magnetic fields inside a wall are not uniform. They fluctuate, overlap, and form structured patterns. A charged particle entering this environment experiences forces that alter its path, drain its energy, or trap it entirely. But neutral particles slip through these force fields with ease. They do not bend, they do not slow, they do not notice. This explains why particle detectors must be massive and dense to catch certain particles. To detect a neutrino, scientists must build enormous tanks filled with thousands of tons of material buried deep underground. Even then, most neutrinos pass through without leaving a trace. The weak nuclear force, which neutrinos interact with, so feeble that matter is almost transparent to them. In contrast, to stop an electron requires very little material. A thin sheet of metal is enough. The difference lies not in the wall, but in the force. This realization overturns the naive idea that walls are passive objects. In reality, walls are active participants in interactions. They exert forces, respond to fields, and exchange energy. They are not barriers by themselves. They are regions where certain interactions dominate. Even at the atomic level, forces enforce rules that create the appearance of solidity. One such rule is the Pauli exclusion principle, which prevents electrons from occupying the same quantum state. When atoms are pushed together, this principle creates resistance that feels like compression. Again, solidity emerges from a force-based rule, not from material fullness. If these rules were different, walls would not exist in any familiar sense. Matter might pass through matter freely. Structures would collapse. The universe would look nothing like it does. The dependence on forces also explains why extreme conditions change what can pass through matter. Under intense pressure, high energy, or extreme temperatures, interaction patterns shift. Particles gain enough energy to overcome barriers or interact through different force channels. Cosmic rays provide a dramatic example. High-energy particles from space routinely pass through Earth's atmosphere, buildings, and even human bodies. Their energy allows them to plow through electromagnetic resistance that would stop slower particles. Again, it is not the wall that fails. It is the interaction that changes. This framework also explains why no wall can block everything. There is no universal barrier. Every wall is selective. It blocks based on force compatibility, not physical thickness. From this perspective, walls are agreements forced by nature's laws. They represent regions where forces align to prevent certain interactions, but agreements can be bypassed by entities that do not participate in those rules. This insight has profound implications beyond physics. It suggests that limitations are context-dependent. What stops one thing may not stop another. Boundaries exist because of relationships, not absolutes. At the smallest scales, the universe is not built from rigid structures, but from interactions layered upon interactions. Forces define behavior. Charges define responses. Matter is not a wall because it is matter. It is a wall because it exerts the right forces in the right way. When a particle passes through a wall, it is not breaking the wall. It is revealing the wall's true nature. It shows us that solidity is conditional, permeability is relative, and boundaries are negotiable under the right physical rules. This is the quiet truth hidden behind every solid surface. The wall is not saying nothing may pass. It is saying only those who interact in certain ways will be stopped. Everything else moves on, unnoticed, through a universe that is far more open than it appears. Light feels intangible. It has no weight, no rest mass, and no visible substance. It moves effortlessly across vast distances, crossing space from the sun to Earth in minutes, slipping through air as if nothing were there. Yet the moment light encounters a wall, it stops. It reflects, scatters, or vanishes into heat. This contrast raises a natural question. Why does something so insubstantial fail to pass through a solid object, while other particles can pass straight through with ease? The answer lies not in light's weakness, but in its strength. Light does not pass through walls precisely because it interacts so effectively with the electrons inside them. This interaction is not accidental, it is fundamental to the nature of light and matter, and it defines how we see the world. Light is composed of photons, which are quantum particles of electromagnetic energy. Every photon carries an oscillating electric and magnetic field. These fields are not passive. They actively influence any charged particle they encounter. In solid objects, electrons are abundant, mobile, and tightly bound within atomic structures. When light arrives, these electrons respond immediately. At the atomic level, electrons are not fixed points. They exist as quantum clouds, constantly shifting and vibrating within allowed energy states. When a photon enters this environment, its electric field pushes and pulls on the electrons. If the photon's energy matches the difference between two allowed energy levels in the atom, the electron absorbs the photon entirely. The light disappears and its energy is transferred into the atom. If the energy does not match an allowed transition, the electron may still respond by oscillating. This oscillation causes the electron to re-emit light, often in a different direction. This is reflection or scattering. Either way, the photon does not continue straight through. It is intercepted by the electron cloud. This interaction happens unimaginably fast. Light does not slow down gradually inside matter. It is repeatedly absorbed and re-emitted or redirected by electrons, giving the illusion of reduced speed. In reality, photons move at the same speed between interactions. What changes is the path. In opaque materials, these interactions are so frequent and so disruptive that light cannot maintain a coherent path forward. The photon's journey becomes chaotic. Energy is redistributed among countless electrons, often converted into heat. The wall becomes opaque, not because it is thick, but because its electrons are highly effective at engaging with light. This effectiveness depends on atomic structure. Metals, for example, have electrons that are loosely bound and free to move. When light hits metal, these electrons respond collectively, producing strong reflection. This is why metals shine. They do not absorb light easily. They repel it through coordinated electron motion. In insulators like wood or stone, electrons are more tightly bound but still responsive. They absorb and scatter light rather than reflect it cleanly. This produces dull, matte surfaces. In both cases, the interaction prevents light from passing through. Transparent materials behave differently, but the same principle applies. In glass, electrons absorb and re-emit light in a way that preserves the photon's direction. The light appears to pass through, but it is still interacting constantly. Transparency is not the absence of interaction. It is a controlled interaction. This distinction is crucial. Light does not fail to pass through walls because it cannot penetrate matter. It fails because it interacts too well. The electron clouds inside solids form an effective net that captures, redirects, or dissipates electromagnetic energy. Now consider particles that pass through walls. Neutrinos do not interact electromagnetically at all. They carry no electric charge, and their weak nuclear interactions are extremely rare. As a result, electrons barely notice them. The vast electron networks that stop light are invisible to neutrinos. Even particles that carry charge may pass through under certain conditions if their interaction probability is low enough or their energy is high enough. Light, however, has no such escape. Its very identity is tied to electromagnetic interaction. This explains why increasing light's energy changes its behavior. X-rays and gamma rays interact with electrons differently than visible light. Their higher energy allows them to penetrate deeper before being absorbed or scattered, but even they are eventually stopped. No form of electromagnetic radiation passes through matter without interaction. This also explains why light defines visibility. We see objects because light interacts with their electrons. If light passed through walls without interaction, walls would be invisible. Vision itself depends on light's inability to ignore matter. The same interaction governs color. Different materials absorb different wavelengths of light depending on their electronic structure. What is not absorbed is reflected or transmitted, producing color. Every shade and hue arises from electrons choosing which photons to engage with and which to ignore. At a deeper level, this behavior reveals that electrons act as gatekeepers between light and matter. They decide what happens to incoming electromagnetic energy. Their arrangement, bonding, and energy levels determine whether light is stopped, reflected, transmitted, or transformed. This gatekeeping is not optional. Electrons cannot choose to ignore light. Maxwell's equations and quantum electrodynamics demand interaction. When an electromagnetic field encounters charge, force follows. This inevitability is what makes light predictable and reliable. In contrast, forces that govern other particles do not guarantee interaction. The weak nuclear force, responsible for certain particle decays, operates at such short ranges and low probabilities that most particles slip through matter unchallenged. Gravity is far too weak to stop anything at atomic scales. The strong force is confined within nuclei. Electromagnetism stands alone in its ability to dominate everyday experience. This dominance explains why walls exist in the first place. It also explains why light cannot pass through them. The same force that gives matter structure also blocks electromagnetic radiate. Ion. Interestingly, this interaction places a fundamental limit on invisibility. Perfect invisibility would require matter that does not interact with light at all. Such matter would also be undetectable to vision, cameras, and most instruments. It would be effectively absent from experience. Ordinary matter cannot achieve this because its electrons must interact to remain stable. Even advanced materials designed to bend light around objects rely on manipulating electron responses. They do not eliminate interaction, they control it. Light still engages with matter, just in carefully engineered ways. This reveals a deeper symmetry. Light defines matter, and matter defines light. Atoms exist because electrons interact with electromagnetic fields. Light exists because charged particles can emit and absorb electromagnetic energy. Neither can exist as we know it without the other. When light hits a wall and stops, it is not being rejected, it is being welcomed. The electrons inside the wall eagerly receive the incoming energy, respond to it, and redistribute it. The wall is not an obstacle to light, it is a participant in light's behavior. This perspective changes how we understand opacity. Opaqueness is not resistance, it is engagement. The more strongly matter interacts with light, the less transparent it becomes. From this view, the inability of light to pass through walls is not a limitation but a consequence of deep physical harmony. The same interaction that blocks light enables sight, warmth, energy transfer, and the very chemistry of life. Photosynthesis depends on electrons absorbing photons. Solar panels depend on the same principle. Human vision begins when photons interact with electrons in retinal molecules. Without this interaction, the universe would be dark in a much deeper sense than the absence of light. Light's failure to pass through walls is therefore not a flaw in nature. It is evidence of coherence. It shows that forces are consistent, that interactions are reliable, and that matter and energy obey shared rules. When we compare light to particles that pass through walls, we are not comparing strength to weakness. We are comparing engagement to indifference. Light engages with matter at every opportunity. Other particles simply do not. In this way, walls reveal the hidden hierarchy of forces. They show us which interactions matter most at human scales. They remind us that what feels solid is shaped by electromagnetic dialogue, not by material fullness. The wall that stops light is not a silent object. It is alive with electrons responding to every flicker of electromagnetic energy. Each photon that arrives triggers a cascade of motion, absorption, and emission. The wall glows, warms, reflects, or darkens in response. This is why light cannot pass through walls, and why it never will. Its fate is sealed by its nature. To be light is to interact, and to interact with electrons is to be stopped, transformed, or turned aside. In the end, light does not fail to cross walls because it lacks permission. It fails because it is too deeply connected to the matter it encounters, and in that connection lies the very reason the universe is visible at all. Human intuition is shaped by survival, not truth. Our sense of reality evolved to help us walk, throw, build, and avoid danger in a world of moderate sizes and speeds. We expect objects to stay where they are unless pushed. We expect causes to come before effects. We expect things to be either here or there, moving or still, present or absent. These expectations feel self-evident, almost moral in their certainty. But the universe does not share our instincts. At the quantum level, common sense does not merely fail, it becomes misleading. The rules that govern atoms and particles are not refinements of everyday physics. They are replacements. They do not bend intuition gently, they break it entirely. One of the first shocks comes from the idea that particles do not possess definite properties until they are measured. In everyday life, a car has a position even if no one looks at it. A clock keeps ticking even in an empty room. But in the quantum world, an electron does not have a precise position, momentum, or energy, unless an interaction forces one to appear. Before that moment, it exists in a state described only by probabilities. This does not mean we are ignorant of the particle's true state. It means there is no hidden certainty waiting to be discovered. The uncertainty is fundamental. The universe itself does not assign a single answer until it is asked a specific question. This idea directly violates common sense. We are accustomed to believing that reality exists independently of observation. Quantum mechanics suggests something subtler. Reality is constrained, shaped, and partially defined by interaction. Measurement is not passive, it is participatory. Another intuitive rule that collapses is the notion of continuity. In everyday experience, motion is smooth. Objects travel along clear paths from one place to another. In quantum physics, motion is not continuous in the same way. A particle does not move along a single trajectory. It explores many possible paths simultaneously, with each path assigned a probability. This behavior is not philosophical speculation. It is required to accurately predict experimental outcomes. When particles interfere with themselves, produce diffraction patterns, or tunnel through barriers, they are behaving in ways that cannot be explained by single, continuous motion. Common sense insists that an object must go somewhere to get somewhere. Quantum mechanics allows an object to arrive without having taken a classical route at all. Time, too, becomes less intuitive. In the macroscopic world, time flows in one direction, ticking forward uniformly, causes precede effects. But at the quantum level, the fundamental equations do not distinguish past from future. They allow processes to run equally well forward or backward in time. This does not mean time reverses itself in daily life. It means that the arrow of time is not built into the deepest laws of physics. It emerges statistically from large numbers of particles, not from individual events. At small scales, the universe does not care which way time points. This challenges the assumption that causality is absolute. While quantum mechanics does not allow information to travel backward in time in any useful way, it does allow correlations that seem to ignore classical cause and effect logic. Entangled particles, for example, remain linked no matter how far apart they are. Measuring one instantly determines the state of the other. Even across vast distances, common sense rebels against this idea. It demands a signal, a messenger, a mechanism traveling between the particles. Quantum mechanics offers none. The correlation exists without communication, without delay, without explanation in classical terms. This does not violate relativity or allow faster-than-light messaging, but it does undermine the idea that the universe is built from locally independent pieces. At the quantum level, separation does not imply independence. Another deeply ingrained belief is determinism. The idea that if we know the present perfectly, we can predict the future exactly. This belief underlies much of classical physics and everyday reasoning. Quantum mechanics dismantles it. Even with complete knowledge of a system's wave function, quantum theory can only predict probabilities, not outcomes. It does not tell us which event will occur, only how likely each event is. The universe does not roll forward like a clockwork machine. It unfolds like a distribution. This randomness is not due to complexity or ignorance. It is irreducible. No hidden variables have been found that restore determinism without contradicting experimental results. Nature itself appears to choose outcomes probabilistically. Common sense struggles with this because randomness feels like disorder. But quantum randomness is structured, lawful, and precise. It obeys strict mathematical rules. What it abandons is certainty, not order. Even the concept of existence becomes ambiguous. In classical thinking, an object exists or it does not. In quantum mechanics, systems can exist in superpositions, combinations of mutually exclusive states. A particle can be here and there. An atom can be excited and not excited. These states are not metaphors. They are physically real until measurement collapses them into a single outcome. This clashes violently with everyday logic. We are trained to reject contradictions. Quantum mechanics forces us to accept that nature tolerates them, at least temporarily. The act of measurement itself defies intuition. Measuring a quantum system does not merely reveal information, it changes the system. The measuring device becomes entangled with the particle, and the result depends on how the measurement is performed. This means that there is no neutral viewpoint from which reality can be observed without influence. Every observation is an interaction. Every interaction leaves a trace. Common sense assumes we can stand outside the system we observe. Quantum mechanics insists that we are always part of it. This participatory aspect leads to paradoxes that have no classical analogue. Thought experiments involving cats, observers, and multiple realities are not whimsical distractions. They are attempts to grapple with the consequences of a theory that works perfectly yet resists intuitive interpretation. Despite this resistance, quantum mechanics has never been proven wrong. It has survived every experimental test. Its predictions are confirmed to extraordinary precision. The discomfort lies not in its accuracy, but in its implications. The challenge to common sense extends to the idea of objects themselves. In classical physics, objects are primary. Forces act between them. In quantum field theory, fields are primary, and particles are excitations of those fields. A particle is not a thing in the traditional sense. It is a process, a localized disturbance in an underlying structure. This redefinition strips particles of their solidity. They are not little balls moving through space. They are patterns of interaction. They exist only insofar as they interact. Common sense wants objects to be self-contained. Quantum mechanics reveals them to be relational. What a particle is depends on how it interacts with other systems. Even emptiness loses its meaning. What we call empty space is not empty. It is filled with fluctuating fields, virtual particles appearing and disappearing, energy rising and falling. This restless background affects measurable phenomena, from atomic stability to cosmic expansion. The vacuum is not nothing. It is the most active state of all. All of this leads to a sobering conclusion. The universe is not obligated to make sense to us. Our intuitions are parochial. They evolved in a narrow band of conditions and scales. When we step outside that band, intuition becomes a liability. Quantum mechanics does not ask us to abandon reason, it asks us to abandon familiarity. It replaces comfort with consistency and expectation with evidence. This is why particles pass through walls, why light behaves as it does, and why matter is mostly empty space. These are not isolated oddities. They are expressions of a deeper truth. The rules that govern reality are not designed for human understanding. And yet, through mathematics, experiment, and humility, we have learned to work with them. We build technologies that exploit quantum rules without fully intuiting them. We trust equations where imagination fails. In doing so, we confront an uncomfortable but profound insight. Common sense is not a guide to truth. It is a survival tool. The universe operates on principles that are stranger, subtler, and far more elegant than everyday experience suggests. Quantum mechanics does not replace reality with mystery. It replaces false clarity with honest uncertainty. It shows us that the world is not built from certainties stacked upon certainties, but from probabilities woven into stable patterns. Walls are solid because probabilities align that way. Light stops because interactions demand it. Particles pass through because nothing forbids them absolutely. The quantum world does not mock common sense. It simply ignores it. And in that indifference, it reveals a universe that is not simple, not intuitive, but astonishingly coherent. Thank you so much for watching. If this video inspired you, be sure to like, share, and subscribe to be inspired from life for more motivational content. And remember, no matter where you are in life, you have the power to change your future. See you in the next video.